Jess, who's studying for her foundation and he's going to get it.
Yeah.
We got, forgotten your name?
Jazz.
Jazz, that's
Just like
right.
music.
Yeah, who's also with us. And anybody else new? Welcome.
I'm Noel.
Noel, pleased to meet you, Noel. Yeah, so great.
Mike Zero Victor.
Victor Oscar Mike.
Voice of Manchester.
Volt ohm meter. That's Voice of Manchester. That's a good one. Yeah. Yeah. Tonight is the first part of a two-parter. So we're going to look at modulation tonight, which is we're going to kind of pitch it at the dead simple level and cover some things that are in the foundation exam and a few bits of things that are in the intermediate exam. 2 weeks time we're going to do part 2, which is more about mixing and stuff like that, which is a bit more intermediate, but you'll still get some bit more understanding out of it if you're doing the foundation. If you want to come along, you're welcome to do so. And on that subject as well, we put in some regular tutorial and operating nights into the calendar now. So we'll get the club gear out, we'll plug it into the aerials. Those of you who want to see what you can work can have a go at working stuff. And if I can get in my garage, I might even bring the FT8 stuff down one night. So if you've never done any of that and you want to have a play with FT8 or whatever else you like. And while other people are doing that, if you're studying for the exams, you've got any questions on any of the topics, you want something going over, just bring your book and bring your questions, and one of us will sit down, we'll go through it with you. Happy to do that. That's what the club is here for, to help people to advance their knowledge, learn more stuff, pass the exams and get on the air. So we're happy to do that also. Linda is still not out of dry dock yet. She's waiting for the test results, and I spoke to her last week and they hadn't got the test results for some reason, so they cancelled her appointment and made her another one for this week sometime. So she's still in limbo waiting to find out exactly what they're going to tell her. But she sends her regards and wishes she could get down the club, and I'm sure that she'll get back eventually as soon as she can. For those who want to know what her state of mind is, she's bouncing off the walls. She's really frustrated and just wants to be able to get out and do things but can't. Last advert, next week we've got a good treat. We've got the chairman of the Bolton Wireless Club, who was involved in the Ukraine relief effort, where they collected up spare gear, surplus gear for the Ukrainian radio amateurs and shipped it over to Ukraine. He was involved in that, and he's got a video presentation for us. So we'll be doing that over Zoom. So please come down, join us, put some money behind the bar, support our patrons. Phil's nodding his head. And we'll put the Zoom up on the big screen so you can see it from here. If you can't be bothered to come down, or you can't get down for some reason, we'll post the link. Look out for your club emails, and you can always join it from home and watch it that way. So I'm really looking forward to that. It's going to be good. So great. Are you ready to launch into this then? Yeah?
Yeah.
All right. Modulation. Basically, if you invent a transmitter that just sends radio frequency energy from one place to the other and does nothing else, you've invented the most useless device that mankind ever invented, because all it does is sends energy and nothing else, and it's useless.
Yeah, like your phone.
Yeah, phones are useless as well. So modulation is the whole point of it. We want to communicate, we want to send information to the other end of that RF link. So modulation, as it basically says, is just the exercise of imposing some sort of wanted signal onto that radio frequency transmission so that we can convey information, be that speech, be that data, be it, well, a number of things that we're going to look at. And that is one of the questions on the foundation exam. Understand what modulation is. That's all it is. It's just a process of impressing some sort of useful information onto that signal, sending it via the signal, by the transmission, and of course being able to get it back at the other end and turn it back into speech or Morse or data or whatever it was that you were sending. So pretty easily. There's different forms of modulation. Each of them have their own characteristics. Some of them are better for some things than others. They have their benefits, they have their drawbacks, so we're going to look at some of those tonight. Feel free to chuck in with any questions and observations that you've got. I'm not the fount of all knowledge here, so always makes me nervous standing up and doing talks, because I'm always like worried somebody's going to come tonight who knows a damn sight more about this subject than I do, and he's going to make me look stupid. But since I'm already stupid, it doesn't matter. Right, so the first and obvious one, and the first one that ever got invented, is the humble Morse code. So all we're literally doing with Morse code is switching the RF transmission on and off with a switch that happens to have a knob on it and be formed into the shape of a Morse key so that a human can use it. But literally that's all we're doing. We're turning the carrier wave on and off using a switch. With Morse code we send a series of short and long pulses, dots and dashes. And if you've got a human at the other end who's trained to read Morse code, they can turn that back into the letters and the words that were sent. So all you Morse students, what Morse letter do we have up there? Come on. Nobody knows.
P.
P. Jim's on it. Yeah. So that is the Morse for P. Dot, dash, dash, dot, or dit, if you're going to do it properly. If Linda was here, she'd have a barbed wire whip out and be chastising a lot of you for not knowing that. And of course, this is effectively the first digital mode. Long before digital was ever a thing, this was actually digital transmission. So when people say, oh, digital, it's not real radio, just tell them to go back to the 1940s when Morse code was invented, because that's digital. It is. So what about Morse code then? Advantages, disadvantages. It's extremely easy to engineer, because basically all that you're doing is turning a transmitter on and off with a switch. Can't get much simpler than that. It's very easy to receive. All you need is a pair of ears and some practice, brain that's been trained to get it, and usually a pad and pencil helps as well, so you can write it down as you're listening to it. Very, very low bandwidth required. It's literally just a single transmission on a single spot frequency that you're turning on and off, and that's it. So it's very, very good in terms of the amount of space it takes up on the radio spectrum. You can fit an awful lot of people working Morse code in an awful lot of small frequency bandwidth, which is why you usually get just the bottom end of all these shortwave bands, and you can get hundreds of Morse conversations going on in that little space. So it's really good on bandwidth, excellent in weak signal conditions. A trained operator can pull a Morse signal out of a noise that's barely audible and can still understand what the person at the other end is saying. So it's very, very good for that. But of course, the speed is limited because you're sending each letter individually, and each letter is made up of several bits, some longer than others, depending on which letter you want. So, I mean, the fastest operators, the marine operators, the really, really good guys, do about 45 words per minute. When we used to have the Morse test in the amateur exam, you had to be able to do 12 words a minute. People generally 20-25 words a minute is a really slick operator on the HF bands, but that's not tremendously fast by today's standards. So it is a bit limited, and of course it depends on how good the operator is. One thing that also comes up on the exam is they want you to understand and appreciate what key clicks are and why they're a problem. So basically, before we'll cover that, if you turn the transmitter on and off too fast, too sharply, those very steep rising and falling edges on the waveform can cause interference. I'm going to jump back and forward between these slides here. So that top one there is like an image of just maybe one Morse dot being switched on and off. You can see it gets switched on. There's the RF being generated and it gets switched off at the end. Very sharp, very steep rise and fall times. Whenever you see very steep rise and fall times, what you've got there is a lot of harmonics being generated. You can ask me why if you like. There's a lot of explanation and maths behind that, but trust me, whenever you see very steep sides on anything, There's a lot of harmonic content there. And if you look at it on a spectrum analyzer, you see all of those harmonics out to the side here. Whereas you should just have that one frequency there and not very much else. You get all this stuff being generated because of those steep sides. If we slow down the rise and the fall, we reduce that muck. So we reduce the interference. So key clicks, those clicks as the thing goes on and off, cause interference. There you go. That's your answer for the foundation exam. That's as much as you need to know. Intermediate, they want you to know a little bit more about it. You can get rid of them using a key click filter, which is basically a very simple circuit there. If you think about it, what do we know from the basic stuff that we've done? Inductors, they like to allow the current to ramp up slowly. So that will slow down the rise if you put a small inductor in it. And the capacitor with the resistor, just to adjust the timing, will slow down the fall. So just by that simple circuit there, you can get from that to that, and you can reduce the interference. So that's key clicks. Comes up occasionally. So you know about it now, you'll understand what it is. That's Morse. There's not a lot more to it, to be honest. Other than it's an awful lot of fun. Once you've learnt it, it gets very addictive. So we move on then to the next thing that was invented, which is good old AM. Amplitude modulation. Amplitude just means the size of something or the value of it. And modulation means we're changing the size. So basically the middle line there, we've got your constant RF signal, the carrier, being transmitted out to wherever it's going. And there's nothing very interesting about that. But if we can impose upon that, the size of it, an audio waveform, which is the top one, we get something looking like this. And at the other end, we can detect that rising and falling value, turn it back into the audio, and we've actually now been able to transmit speech. They always draw the diagrams like this, and they always put this line on the outside. And it's not really there. That's just them attempting to show you that what they're doing is imposing that on that. But if you were to look at this in real life, all you'd see is the RF, and it gets bigger, and then it gets smaller, and then it gets bigger, and so the volume, if you like, is just being turned up and down very fast. It's just varying with the speech. So they're turning up and down the volume of the transmitted RF signal, if you can understand it that way. What do we know about that then? Well, there's a couple of ways of doing that. This is one simple way. Sorry about the hideous diagram, but it's the best I could find. The speech coming from the microphone is on the far left-hand side. We've got a mixer or a modulator in the middle, and an oscillator here generating the RF signal. And you impose one on the other, and you get this varying amplitude of RF signal coming out. Amplify it, stuff it up a tower, and send it to people. That's low-level modulation because we're doing it before the amplifier. The old-fashioned brute force and ignorance method was to do it right here at the amplifier, and I'll show you that very shortly. So that's AM. That's all it literally is. There's more to say about it, of course. Advantages, disadvantages. It's reasonably simple to transmit that. Quite easy to build an AM transmitter. But the transmitter's not very efficient. Because if you think about it, you've got that stonking great carrier being sent all the time. Whatever you're doing, you're radiating all that energy for nothing. And so your transmitter, all the valves and the parts you select have got to be able to provide all that power. And all that power is coming out of your electric meter and going on your bill, even when you're not even sending any speech. And of course it's getting hot, so it's going to need a fan or something to cool it down. So the whole thing's not very efficient, and you've got a lot of overhead in there just to be able to send that information. But it works, and it's simple. Dead easy to receive at the far end. It's great for communication purposes, not so good for high quality audio, which is why if you listen on medium wave, when there used to be things on medium wave, that was kind of designed for people with a little plastic transistor radio stuck on the ear, listening to the commentary on a football match. It wasn't designed really for sending classical music. They did it, but it wasn't very good. That's why they invented other things to do that better. The other thing about AM is it's susceptible to interference. If you think about this, the information is being conveyed by changes in amplitude. And spikes, clicks, noise, crackles, they're all amplitude signals. So as soon as you get any interference, noise, spikes, clicks, hideous hash coming from electric motors or car ignition systems or whatever, they're going to come thumping straight on the top of your signal, and they're going to interfere with the speech or whatever you're trying to send. So it's actually susceptible to that kind of interference. Let's look at how we do it. That's the brute force and ignorance method of transmitting AM. Much simpler than it looks. At the far side there, all we've got basically is a source of RF energy. That is just basically a push-pull output stage. It's the final stage in the transmitter. The phase inverter there, so you're driving the two transistors out of phase through the winding of the transformer. We've looked at that before. And all we do is the actual power supply to that circuit, we just stuff it through a transformer and bang audio into it. And as the audio comes in, it will partly, at one cycle, it will increase the voltage. At another cycle, it will tend to reduce the voltage. So you're literally by the brute force and ignorance method, imposing modulation on that RF that's coming out. And you get something like that. You may see comments about modulation depth. I don't think they really go into it on the foundation exam. But obviously, the most that you can go is when that actually touches the 0 point at the dip in the curve. If you try and drive it any harder than that, you're going to get a flat piece in here, and that's going to cause distortion. So 100% modulation is the most that you can go. And they usually have a scope or something like that just to be able to watch that to make sure you're not over-modulating it. Again, sudden transitions and flat lines cause interference. It causes problems and muck. So you don't want to do it. Receiving AM, very simple. You basically just need a diode, a resistor and a capacitor, and you've got it. That's all you need for an AM detector in its simplest form. Shows you how it works there. The amplitude modulated carrier frequency is there coming in on the left hand side. The diode, literally, we know it's just an electrical one-way valve. It chops off half the waveform, because the bottom half can't go through the diode because it's negative, the top half can because it's positive. So what we've got there is we've got our audio waveform again, but we've still got all the RF in it. Literally the capacitor and the resistor just filters out the RF, so you get the audio out the other end. Dead simple. And in fact, if you just modify that circuit slightly, make that a tuned circuit there and connect an aerial onto it and a good earth, and a pair of crystal earphones, you can actually pick up AM radio stations even without a battery. That's just a crystal set, and it's literally all you need, about 5 components, and it will work. So back in the World War II, when there was lots of AM stations and things broadcasting, people in prisoner of war camps were scrounging bits, and they were building simple crystal sets like this, and able to actually listen to the news that was coming from home and get secret messages and stuff. AM, dead simple. Not too great for some things, but dead simple. Before we leave it, let's just look at the frequency spectrum of AM, because that's going to lead us on to something else very shortly. So what are we talking about when we talk about the frequency spectrum? If you were to look at it on a spectrum analyzer, you would see in the center of the display the carrier signal, FC. And if we were to put into our AM modulator, say a 1 kilohertz tone, nothing else, just a pure 1 kilohertz tone, something like that. Don't know whether that was 1 kilohertz, but a tone, a sine wave. What you would see is you'd see the modulating frequency plus the carrier, and you'd see that minus the carrier. So you'd see an upper tone line and a lower tone line, spaced 1 kilohertz away. So if your center frequency was transmitting on 7 megahertz, for example, you get 7.001 above it and 6.999 below it, 1 kilohertz difference. That's actually, you might be thinking, why is he telling me about that? That's a bit confusing. But try and at least keep space in your head, and what we're going to do next might make it make more sense to you. If we were then to replace our 1 kilohertz tone going into our transmitter with somebody babbling away with speech like I am, that contains all kinds of different frequencies that come and go at random, and there's harmonics of frequencies and all sorts of things going on. So instead of a single tone, you literally get a band of tones, a side band, if you like, because it's at the side of the carrier. And just like that, you get one on this side and one on that side. Anybody heard of upper side band before and lower side band? We're going to come to that in a minute. You'll see how it fits in. So I showed you that because that's quite important. And when we get onto SSB, which we're going to do next, people are going to start having a mental problem with that idea of a carrier. And if you don't think about it in these terms, you will never understand what's going on. So, you ready to take a big leap? Yeah? So single sideband, we'll start off with exactly the same signal that we just transmitted. That is an AM signal. We've looked at that. Everybody understands that. It's quite simple. Well, as we said, it's inefficient. You're transmitting that big carrier there, and when you're not transmitting any audio at all, you're still transmitting that carrier, 400 watts of it or whatever you're doing. You've got to pay for that. You've got to generate it. You've got to have a transmitter big enough to do it. It's a bit wasteful. So when people were trying to improve AM, one of the first things they said was, I wonder if we can get rid of that carrier. And that's exactly what they did. If you can somehow filter the carrier out by some magic means and not transmit it anymore, what you have is double sideband, which is another modulation mode. That's literally double sideband. The two sidebands but no carrier. Interesting. People sometimes think of this thing of the carrier, they understand AM, they understand that we're imposing the modulation on the carrier, and then you tell them, oh yeah, now we're getting rid of the carrier. And they go, yeah, but how does the modulation get to the other end? Without the carrier, there's nothing to carry it. But this is where the problem comes in. That term carrier is a little bit misleading. It's not actually carrying anything. And if you look at the diagram, you can see what's actually happening. The modulation that's being imposed on the carrier is generating, relative to the carrier in frequency terms, these sidebands, and the actual information is in here. It's not there. That carrier is just a reference point, if you like. It's a zero mark from which these can spread out and do their thing. Hopefully that's clear. If penny hasn't dropped, come back and talk to me again and we'll draw some more diagrams until you get it. Because that's something that people fall over regularly. They go, I don't get this carrier thing. How can you get rid of the carrier and still transmit? Let's just assume we can. So we've got double sideband with no carrier. That's become more efficient already because we've got rid of all the power we were pushing out in that carrier. But we've got, the information is duplicated. Well, why don't we get rid of one of them as well? Well, while we're at it. So we could get rid of the lower sideband by a suitable filter, and now we just have upper sideband, which is literally just that upper sideband. No carrier, no lower sideband, just the upper sideband. Or if you want to do it the other way around, of course, you could just transmit the lower sideband and not the upper sideband. And that's what you'll find on the shortwave bands, upper sideband and lower sideband. By convention, lower sideband is always used below 10 megs. Why? Nobody really knows. It's just a conversation. Just remember, 10 megs and below, lower sideband. You can think about it. 10 and below, lower than 10, you use lower sideband. Higher than 10, you use upper. Why? Nobody knows, just because that's the way the world does it. But that'll get you an extra tick on your exam and you'll be one tick closer to passing. Also, if you go on the shortwave bands, use upper sideband on 80 meters, for example, you'll find it a very lonely experience because everybody else will be using lower sideband and nobody will talk to you. SSB, advantages and disadvantages. As we've said, the transmitter's more efficient. The bandwidth is lower, remember? Look at all that bandwidth we're using there for AM, and look how much less we're using when we just send sideband. It's better than AM under noisy or weak signal conditions precisely because the bandwidth is smaller. So there's less signal to get interfered with. Simple. More difficult to engineer, both for transmit and receive. There are ways to do it. We'll have a look at it just briefly. Not expected to know this for the foundation exam at all. You barely touch on it for the intermediate, but just for the sake of clarity or confusion, that's an SSB modulator by some German guy. Designed it in 2022. It looks hideous. It's not. That side there, you've got a microphone input. You've got a 741. He's got a typo there. He's called it 714, which is literally just an audio amplifier chip. That's all it's doing, is amplifying the signal from the microphone. Then here you've got an MC1496, the ubiquitous balanced modulator chip. So magic happens inside that chip there. And what it does is the local oscillator signal, the RF, is coming in here. And the way the modulator works, it's modulating it, creating double sideband, but notching out the carrier. So we've got rid of the carrier at that point in the balanced modulator. And then to get rid of the sideband we don't want, we've got simple crystal filter. And if your balanced modulator is set just right, and your crystal filter is set just right in the right place on the diagram I showed you of the frequencies, you can filter out the sideband you don't want and just transmit the one you do. And that's basically how SSB is generated. But as you can see, there's a lot of tweaks and things to get right, and it's a little bit more complex to actually get that right and transmit something intelligible than it is just to build an AM transmitter. But it's eminently doable. Yaesu and Icon, they do it all the time, and lots of other people do it. The late Stephen G30AG actually built his own SSB transmitters. He built a number of them out of bits. Very clever chap. So yes, it can be done on your kitchen table as well. If you're interested in a balanced modulator, that's more or less what's going on inside it. Looks a little bit like a weird bridge rectifier, but you can see the idea of the balancing coming in here. Everything is balanced. There's your audio coming in. That at the side there is just an oscillator generating the RF, and coming out here is your double sideband signal, which then goes into a filter to get rid of the sideband you don't want. Probably as much as you need to know about how SSB is generated. In fact, probably more than you need to know about it, to be honest. On receive, looks vaguely familiar, looks similar to the balanced modulator. That's because it's a balanced demodulator, and it's doing basically the same thing. This thing here to the local oscillator, we're injecting an RF signal in the receiver into this circuit to get the audio to come out. And what we're basically doing is we're putting the carrier back. Yeah, because all of this audio in here only makes sense when you can reference it to its point of origin. So we put the point of origin back, and if we set that oscillator to exactly the right point, the speech becomes intelligible again. On old radios, you'll see it described as a BFO, beat frequency oscillator. That's not really for SSB. That's a beat frequency to give you a note to be able to read your Morse code. The modern term, and the one they expect you to know for the book, is CIO, carrier insertion oscillator. And that's literally what it's doing. It's an oscillator that's generating the carrier that you are inserting at the right point to be able to demodulate your SSB. So there's another little tick for your exam. CIO. Good?
Yeah, very good.
Everybody's quiet.
Yeah, no, we're listening.
Right, you ready to go on to something else? We're about to change direction here, yeah? FM. Everybody knows what FM is because every radio station you listen to goes blah 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 radio, FM, stereo. So FM is a common ubiquitous thing to us here, but it's a different way of doing it. In FM, the amplitude of the carrier signal stays the same. It's always the same value. What we do is we slightly modulate its frequency in sympathy with the audio that we're transmitting, and that's how that works. You might think, why do that? Well, we'll come on to that in a minute. The amount of frequency variation is called the deviation. So you think about it, the carrier is on whatever frequency it is, 101.1 megahertz, classic FM, for example, and if it moves 25 kilohertz either side, that's 25 kilohertz deviation. It's just literally how much it moves because you're modulating the frequency. And again, that's literally what is happening. That there is attempting to show you a waveform that's been slightly changed in frequency. It's not a very good drawing, but in spectrum terms, you can see what it looks like. So if you imagine what's happening there, you've got the carrier, which is here, which is my finger, and it's just moving up and down very, very quickly, depending on what the audio is that's been put in. The frequency is changing. And when you look at it on some sort of scope or diagram, you see this spread looking thing, and it looks like that. What's actually happening, if you get behind the scenes, and this is where we're going off into the deep end for the intermediate, is you've got actually a whole series of sidebands being generated. And each of the audio frequencies is generating its own set of sidebands, and if you put all those together on top of each other, you see what looks like a continuous spread spectrum. But it's not actually. What's actually happening is you've got a whole series of sidebands being generated in there. And that's important later on if you go into doing more detailed stuff on how FM works, but we'll leave it there at that point. It's not exactly the same thing. Welcome, come on in, join us. So, FM, we're clear. It's pretty simple actually, yeah? Advantages and disadvantages. Well, it's more efficient than AM for a start, but not quite as efficient as SSB, because if you think about it with SSB, when you're not transmitting any audio, you're not transmitting any RF energy at all, because the sidebands only appear when you speak. With FM, the carrier is always there. So you've still got that overhead, but it's better. It's easy to engineer for transmit, it's bog simple to be honest. Moderately difficult on receive, probably not as finicky as SSB, but similar sort of level. Because you've got that infinite series of sidebands being generated, and you can take as much frequency as you want, you've actually got better frequency response, especially at the higher frequencies, modulation. So your triangles, your tambourines, your really high notes and everything can survive the modulation process a lot better on FM, which is why they use it in preference to AM for high quality music and broadcast audio and stuff like that. What else is there to say? Yeah, it's more resistant to natural noise. Remember we said all those noisy pops, clicks and crackles are amplitude modulated. Well, this is not listening for amplitude modulated signals. In fact, a good FM detector will actually actively eliminate them and ignore them. So all that amplitude modulated noise that's out there in the world tends not to affect your FM signal. So you've got a much better noise-free environment as well. Higher quality audio, less interference. What's not to like? Well, some of the music they play on there for a start, but the way it is. On transmit, easy enough, as I said. Again, this looks complicated. It's not. All this basically is an RF oscillator circuit, and you'll notice right on the far left-hand side, across the tuned circuit here, we've got a variable capacitance diode, a varicap diode, and all we're doing, we're putting the audio signal in there, we're varying the DC voltage across that diode. With a varicap diode, you vary the DC on it, its capacitance changes. So we've got effectively an electrically operated little variable capacitor across the tuning circuit. And as we tweak that with the audio, it'll move the frequency of the oscillator. Ta-da! You just generated FM. Dead easy. Similar things, you can stick a varicap diode across a crystal, there's all different ways of doing it, but fundamentally that's what you're doing. Receiving looks similar again. There are various ways of doing this. This is one. This is a ratio detector. There's also a thing called the Foster-Seeley detector, which has a wonderful name and looks very similar to that, to be honest. It's very slightly different. And all that's happening here is when you've got a quiet carrier coming in with no audio on it at all, what comes through here is completely balanced. So you get a voltage being generated across there, and that gives you zero output. When the frequency changes, this extra winding on the transformer begins to get one side or the other out of phase, depending on which way the audio is going, and that allows this balance to disappear, generates an output, and that's how you get the audio out of it. So that's as deep as I'm going to go into explaining that. There's loads of stuff on YouTube if you want to know how this works, but that's basically what you're doing. That gives rise to something interesting because you get this thing called a quietening effect on FM. Because if you think about it, when you've just got a carrier with no modulation, no audio, the presenter is not speaking and the record has just finished, you're transmitting silence. On AM, you can hear all this sort of stuff going on in the background. On FM, it sounds quiet because you're detecting it in this way. When you've got a carrier, you've got zero audio output. So with a strong FM signal, you actually get this quietening effect where when you tune a receiver into it, it goes quiet. And it's like, hey, this is really good. You know, I've got a nice quiet background to listen to now. And they also talk about the number of dBs of quieting that you get, which is just basically how strong the signal is and how quiet it goes when you tune in properly. So you may come across that term quietening, and that's what this is. You don't get it on anything else but FM, but it's important. The broadcast people love it. So we're nearly there. Other modes, we'll just touch on some of them. Basically, we've got Morse code, CW. Again, that's the world's worst term, isn't it? CW, continuous wave. It's not continuous. You're turning it on and off with a switch. But they call it CW, so just remember that is Morse code for the amateur exam. We've got AM, amplitude modulation, which nobody really uses anymore. We've got SSB, which everybody uses, and you've seen how that's basically generated. We've got FM, which everybody uses on the VHF, UHF bands. And then we've got other stuff that you might hear on the bands if you're tuning around. RTTY, radio teletype. Basically, that's a digital mode, and it's just using characters using the old board teleprinter alphabet. So it uses one tone for mark and a different note for space. So if you listen to it on the bands, it's sort of going warbling away between two notes. And if you hear something like that, it'll be RTTY. Used to be done literally with mechanical teleprinters. When I was young and foolish, I had one. They're literally that big by this big, and when you put it on the table, it's got a big motor in it that drives all the mechanical mechanism, and your table goes chugga 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 chugga. Even a good table would do that. My mum wouldn't let me keep it. It made too much noise in the back bedroom, so I had to get rid of it. These days, nobody does that. They all use a computer, but the modulation method is the same. Slow scan television. Similar thing, except we use a range of audio frequencies. So for example, the lowest note in the frequency range in the audio might be black. The highest note would be white, and every different shade of white in between has its own frequency. So as the lines scan across the picture and it goes, oh, that bit's black, oh, white, grey, black, the note will change. It's transmitting the information to allow the device at the other end to build up the picture. It's slow scan because it uses audio frequencies to do it. It takes about, is it 7.5 seconds or something to build up a frame? So you can send slow pictures, you can send a mug shot, you can send a picture of your garden or your dog or your aerial or whatever, and people do this on the shortwave bands. It's quite popular. So you may come across that one. Fast scan TV, of course, amateurs do that as well, and that's exactly like the old TV transmissions of yore used to be, usually on VHF or UHF, and they're literally sending old analog TV signals which you can pick up on a computer or even on a telly. That's the way it always used to be done. And then of course we've got digital modes, and it's all very similar. People fall over digital, they don't understand it, they think it's some great arcane thing. All you're doing is modulating your transmitter with a digital signal instead of an analog one. So instead of a voice, instead of warbly tones to send a picture using slow scan or something, you know, audio notes to do teleprinter, you just put in a digital signal on there. That can be digital as in a computer at the other end is going to read it and do something with it, or it can be digital voice. You know, you speak into your microphone, something in your set turns that into a digital bit stream. You then put that bit stream onto your radio and transmit it, and at the other end you decode it and you get the voice back. It's no different. It's exactly how it works. As I said, there's different ways of doing it. Frequency shift keying is basically what RTTY is doing. It's just using two different frequencies for one state or the other state. There's loads of different schemes. There's phase modulation, there's quadratary phase modulation. There's more different types of digital modulation than I understand, to be perfectly honest with you. But they're all out there on the internet and you can find out about them. Some of them are proprietary. There's C4FM. Yaesu System Fusion uses that. There's D-Star, there's loads of others. Just different schemes of encoding that digital information onto your transmitted RF to do something useful. Well, advantages. Well, you can put data along with your digital voice. You can send a little picture of yourself. You could send your own call sign embedded in there. You could tell people what the weather is like at your location, or along with your signal you could be sending, this is the level of my battery and it's running out and so I'm going to get cut off soon. You can embed all sorts of things, useful bits of extra information along with that bit stream. You could also do store and forward routing, so you can do things like APRS, for example, you know, where you can actually send, here's some information, it's supposed to go there, and something can pick it up and go, oh, that's not actually for me, that's for him, I'll retransmit it. So you can do all sorts of things that you can't do with basic analog modulation. Some schemes provide extremely good audio quality. There's voice wide on Yaesu System Fusion, which is like for people who really want to have luxurious, you know, armchair audio. You know, you can do that. Other schemes provide exceptional performance under weak signal conditions. I'm thinking FT8, for example. It's just another digital protocol for sending information, but that is so good, and I'll tell you, it is that good that I've been on 10 meters running FT8 and I've listened and I cannot hear anything. It's like there's nobody there, and yet the computer is pulling signals out of the noise that I can't even hear and decoding them. That's how good it is under weak signal conditions. Even better than Morse. It's phenomenal. When you see it working, it blows your mind. You go, what is this witchcraft? You know, but hey, I'll take it. If it's a contact, I'll have it. So that's your digital stuff. There's not really much more to say. Just to come back to the beginning, all of this is just to convey information. All you're sending is RF, you're wasting your time. So there's all these different things. When do you prefer one over the other? Well, I'd use the one that most other people are using, because then you'd have somebody to talk to. On the higher frequency bands, VHF, UHF, you'll find a lot of people running FM. You find some people running AM still. There are out there, especially on 4 meters. I've got an AM transmitter on 4 meters, if anybody wants to do something silly. Amateur TV, that's up there. People use SSB on these bands, people use Morse. The lower bands, they don't tend to use FM because you don't have enough bandwidth there. People started using wide FM signals, you pretty quickly fill up the band and people will get cross because nobody else will be able to get a word in edgeways. So they use more efficient modes on the shortwave bands like Morse code, SSB signals, FT8, things like that are used down there. But there you go, that's basically your overview of modulation, and I hope it was useful. Now the slide that I dread. Anybody want to come back with anything? Anything that wasn't clear that you want to go over again? Or, yeah, go ahead.
Oh, we don't mind.
I don't mind.
The FM detector that you showed, I noticed it didn't show a squelch, but it looks really interesting. And I was thinking, is it a narrowband detector or a wideband detector for FM? Is it
can.
basically like, and it maybe if it was on wide band, it'd be on band 2, you know, like 88 to 108, but if it was on the bars, it's more like narrow bandwidth, because if you look at an amateur transmission, I think,
Yeah.
roughly it should be 2.5 kilohertz for either way
Yes.
of what you're transmitting, not right, so it should be anyway, with
Yeah.
that sideband. You know, the modulation was good, but another thing you didn't tell me is if you overdrive that variant carefully, you may want a sideband, overdrive it more, not feel more than that than AM, you know. So it depends how you strike the oscillator as how you do it. But the only question there was the FM detector. I've seen things like in illustrations before, but I know a constructive one like that.
Yeah.